All right, we're going to move on today to lesson 10.3, which is over linear, exponential, and quadratic models. Our learning target is to determine which model, linear, exponential, or quadratic, fits best in a set of data, okay? So first thing you're going to look at here is just matching the graphs to what they look like. So we've talked about this a lot over the past months, right? Matching each one up and making sure we know which one is which. One we're probably most familiar with is linear, which always makes a straight line. So this guy's here, okay? And then the formula that goes with that. So a linear function we know or should know by now is y equals mx plus b, okay? Our next one is a quadratic function, and our quadratics always make that U shape, okay? And a quadratic is our factoring stuff. So that was ax squared plus bx plus c. And then our last one that we have is exponential. And exponential we just talked about the other day in our notes, which makes that curve. And an exponential, like we talked about in our geometric sequences, is going to be f of x equals a times b to the x as your formula, okay? So you're going to determine which type of function represents the data, okay? Determining which function type represents each one. We're just going to talk about how can you look at a table of values and tell if it's linear, exponential, or quadratic, okay? So the first thing we're going to look at is we always want to make sure that your x values are always increasing only by 1 each time in the table. If they're not, it's going to throw off what our numbers are doing on the right side for the y. So always make sure x values increase by 1, okay? So once you check that, then you're going to go over on the right-hand side and look at the values that you have here. And just like we talked about with our sequences, we're going to go from the bottom to the top, okay, or backwards, and we're going to subtract. If it's linear, then it's going to be subtraction just like our arithmetic functions were, okay? So, or arithmetic sequences, sorry. So 7 minus 5 is 2. 5 minus 3 is 2, 3 minus 1 is 2, and 1 minus negative 1 is 2. Okay, so if it's linear, okay, you can subtract from bottom to top. And get the same common difference. Okay, just like arithmetic sequences. All right, so for this part, we're going to have that m equals 2, like for our slope, right? Our y-intercept would be here. That's 0, 3. So b equals 0, 3 for where we're starting from. And so if I'm writing an equation for linear, it would be 2x plus 3. Okay? All right. So checking that it has by 1 on the x's, and then on the y's, if it's adding the same thing every time, it's going to be linear. Okay? So then for quadratics, what we have is a second difference. So again, making sure that these are all increasing by 1, and they are, okay? So all that's plus 1 plus 1. Then looking at finding the second difference. So quadratics use a second, oops, messed that one up, sorry. Difference. I'm going to show you what I mean by that, okay? Second difference means that we subtract twice. All right, so I'm going to subtract like I did on my first one, just like with linear, okay? Up, 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 up here, all right? And every time I subtract here, it's different, and it's supposed to be. So this one's 18, this one is 14, then I have 10 here, and then I have 6 on this one, okay? The second different means that you're going to go again with subtraction and do it another time. Now, when you do it this time, all of your numbers should be the same for the common difference, 4, 4, and 4. So that second difference is where we have the same number, and that's where all the values are going to be the same. That's how you're going to know it's quadratic. So if you subtract once and it doesn't work, try subtracting again to see if it's quadratic for that second difference, okay? The third one then is exponential. And for exponential, we're doing the same exact thing. We're checking to make sure that they are all increasing by 1 on our table over here for x's. And then just like we talked about with our geometric sequences, exponential is division, right? So we're dividing because the actual function is multiplication. So 16 divided by 8 gives me 2, right? 8 divided by 4 gives me 2. 4 divided by 2 gives me 2, and 2 divided by 1 gives me 2 again. Okay? And you can write them out this way if you want. 16 over 8 equals 2. 8 over 4 equals 2. 4 over 2 equals 2. And 2 over 1 equals 2, right? So all ratios are the same. Okay? That's how you'll know it's exponential. All right. So moving into the first set, I want you to stop and you give it a try. Tell me if each one of these is linear, quadratic, or exponential. Okay. Pause the video if you can and see if you can get the right answer here. Okay. All right. So we have this one, you should be subtracting to start. So 50, negative 50 minus that gives you negative 21. Subtract here and we get negative 15. Subtract here and we get negative 9. Subtract here and we get negative 3. So it's not linear because the first round isn't the same. If I go again, I'm going to get negative 6, negative 6, and negative 6. So the second difference is the same, which means this one is quadratic. Okay? The next one here, you can start with subtraction. This one would be 216. This one is going to be 72. This one is going to be 24. And then we've got 8. So it's not linear. If I subtract again, I get 144 for this one. And then I get 48 for this one. So it's not quadratic because those aren't. So now I got to divide and get my ratios. So 324 divided by 108 gives me a ratio of 3 to 1. And then if I do 108 over 36, I get 3 to 1. 36 over 12 gives me 3 to 1. And then 12 over 4 gives me 3 to 1. So this one is exponential. Okay? All right, so next part, just to kind of applying what we've learned here. All right, so we have the owner of a framing store tracks the cost of bubble wrap for packing pictures like the one shown. Determine whether a linear, exponential, or quadratic function model best represents the data. All right, so again, same thing. Now, what we talked about earlier was making sure that all of these increase by 1, and this does not. These are all going up by 6 every time. So we have to be making sure they're all the same thing, right? That our ratios are the same. If I do this one back to back, I'm going to have that this is 0.53. This one is 0.42. This one is 0.31. And this one is 0.21 when I subtract. So it's not linear, right? Because it's not the same one. If I do it again, I get 0.11. Then I get 0.11 again. And then I get 0.10. Now, this is all real life data in cost. So these numbers have probably been rounded, which means it could be off by just a little bit. But this is pretty darn close. We're off by a penny, which means we are going to call this good for being quadratic because it's almost the same and human error is going to have a little bit of it in there, right? So example 3, you're going to try same thing. I want you to figure out which one it is, pause it, and see if you can write me a function. Okay? So hopefully you have paused and come back. When we subtract here, we get negative 10.6, and then we get negative 10.5, and then we get negative 10.6, and then we get negative 10.5. Okay, so if that's the case, oops, this should be a 6 too. I'm sorry. If that's the case, all of these are the same again, except for this guy is off by 0.1, a tenth, right? So again, we're going to call this good, and this is going to be linear, all right? If you wanted to write an equation, here's your b, right? Here's your slope, your m. So I've got y equals negative 10.6x plus 100 as my equation. Okay, last one here, making a table to compare linear, exponential, and quadratic growth. All right, so for this one, we have that the population models for 3 cities are on the graph based on the data over a 5-year period. If the populations continue to increase in the same ways, when will the population of city C exceed the population of the other 2 cities? So the first thing you can do is do it by hand, which means you're going to make a table of values. All right, and then you're going to do one for each one. So here's my X. If I want to do the next 5 years, I would go 7, 8, 9, 10, and 11. Okay, and then I would do it for each one of the graphs up here. So f of x was 3.2x, right? Then I have my g of x in blue, which is 0.25x squared. All right, and then in green, I have city C, which is 2 to the x minus 5 power. All right, so all you're doing, you guys, is plugging in your x values, right? Each one of these x values is going to go in to these equations for x using your calculator, and you're going to write down the values that you have. So if I go down, I did this on my calculator earlier, so you guys could take a moment and type these in. 25.6 so that you know that you got the right answers instead of just following along on here, okay? For blue, in the g of x, I got 12.25, then 16, 20.25, 25, and then 30.25. And then for the green, I got 4, 8, 16, 32, and 64. So the question is, when will city C exceed or be bigger than the population of the other 2? Well, you can look here. 4 isn't bigger, 8 isn't bigger than those, 16 isn't bigger, 32 is not bigger, it's the same. So the next year, it's 64, and it's bigger than this one and this one. So year 11 is when it will actually exceed the amount, okay? So doing it by hand, you can look at it that way by plugging in the values for each one. The method 2 is to actually use Desmos, and what you would do would be to type in all 3 equations into Desmos, okay? And then see when city C surpasses or goes above the other 2. Okay? All right, let us know what you have questions about.